Okay, this is an extension to an earlier question in which force F is applied to a rod XY. The rod is uniform, so the weight acts through the center. Okay, firstly, although it is not obvious, besides these two forces, there is a third force exerted on the rod at this end. Right, so there is a force exerted, and of course this force is exerted by the wall on the rod, right? It's really quite obvious because first of all, okay, what is the direction of this third force exerted by the wall on the rod? First of all, we notice that this force F has a horizontal component. Very obviously, this force F will tend to pull the rod to the right, and we notice that the rod is not moving, it is in equilibrium, right? So since there's a force that is trying to pull the rod to the right and the rod is not moving, it is in equilibrium, the third force exerted by the wall on the rod at this end must have a leftwards component, right? So this force must look like this, right? Part of this force must look like this, right? So this force that pulls the rod to the left will balance this force F's tendency to pull the rod to the right. Okay, so we know that the normal component must face to the left. Right, so we have figured out the horizontal component and it is pointing to the left. What about the vertical component of this third force exerted by the wall on the rod? Well, it's a little bit hard to figure out because there's a force W that tries to pull the rod down, and this force F tries to pull the rod up. So it's very hard to figure out whether this vertical force at X is pointing upwards or pointing downwards. Okay, one way out is to consider the moments about the point Y. Okay, if you consider the torque of the forces about point Y, firstly F passes through Y, so it does not exert any moment about Y. Its moment about Y is 0. Okay, W on the other hand will tend to exert a anti-clockwise moment about Y, right? So if you take Y as the pivot, then W, the weight, will tend to cause the rod to rotate anti-clockwise, taking Y as the pivot, right? It should be quite obvious. Okay, so but we notice that the rod is not rotating, right? So since the rod is not rotating, there must be a clockwise turning effect that balances this anti-clockwise turning effect, and the only force that we have not considered is the force at X, the vertical component. So the vertical component at X must be pointing upwards. Okay, so the remaining vertical component at point X must point upwards. Okay, and so this will exert a clockwise turning effect that balances this anti-clockwise turning effect. So we have managed to figure out the horizontal and vertical components of the force exerted by the wall on the rod X at the point, on the rod at the point X. Okay, so the third force would have a leftwards component and a vertically upwards component. Okay, so I'm going to call this third force F prime. So this F prime must act diagonally upwards to the left, right? Because it has a leftwards component, it has an upwards component, so it must point somewhere along this direction, diagonally top left, right? But what is the exact direction? We cannot just have a vague direction, a general direction. We need to know the exact. Okay, so now we are left with finding the exact direction. We know that it is pointing somewhere to the top left, right? So now we have to figure out. And in a case where, in any problem where there are only three forces acting, the three forces, there's a technique which I will show here. Right, so first of all, we notice that the rod is not rotating, it is in rotational equilibrium, right? So the three forces F, W, and this third force, this red arrow, must exert zero moment about any point. Any point. We can choose any point, and if we calculate the moment, we will get 0. Okay, so since we can choose any point, why not choose a convenient point? Let's choose the point of intersection of W and F, right? Which I call Z. Okay, so I'm going to choose this convenient point as the point about which we will calculate the moment. Okay, one thing we notice is that F and W both pass through this point Z. Therefore, if we calculate the moments of these two forces about point Z, you will get 0, right? Because F passes through Z, so the turning effect is 0. F also passes through Z, so again the turning effect is 0. And since we know all three forces, the total moment is 0, the third force must also pass through Z. Okay, so this third force here must pass through Z. So that's the technique of finding the direction of forces in the case where there are only three forces acting on the body, right? So the third force must pass through Z, right? So this must be the direction. And therefore we have managed to figure out the direction of the third force F prime. So we have managed to figure out, so the doubt has been removed. And of course, F prime is the resultant of the two forces we found earlier, this force and this force. So this will be the vertical component of F prime, and this will be the horizontal component of F prime as shown here.